Hi, this is the video for section 1.6, the final section before the problems of chapter 1 of A Student's Guide to the Schrödinger Equation. This whole section is about using the inner product to find components. You've already seen how this works for vectors. Back in section 1.1, we mentioned that you could find a sub x by dotting the Cartesian unit vector I hat into A. Same thing for ay and az. And that's a way, if you have the vector A and you know your basis vectors, I hat, j hat, k hat, you can find the components ax, ay, az. A little shorter way of writing that is a sub I equals epsilon sub I with a little caret hat denoting a unit vector dot A, where I can be 1, 2, or 3. And those epsilons just represent I hat, j hat for epsilon 2, and k hat for epsilon 3. The good news is the same technique works if you have a generalized or an abstract n-dimensional vector, which we're going to represent by ket A. So here's the components of that thing. Notice we're taking each basis vector, which we've called epsilon sub I. Notice, by the way, that this is a little arrow hat over epsilon sub I rather than a caret hat. We're dotting each of those basis vectors into A, and we're dividing by the square magnitude of the basis vector. In Dirac notation, that looks like this. Well, that's a little different than the expression we just saw. If I clean this up a little bit, you can see that we have the dot product, but now we've got this denominator term. And what's all that about? Well, remember, when we did this version, we had unit vectors. The epsilon sub I here had the caret hat on. These are orthogonal, they're perpendicular basis vectors, but they're not necessarily unit vectors. And this shows why it's necessary to divide by the square magnitude of those when you want to find the components. So here's vector A. Here you see one of the basis vectors. This one's pointing along the x-axis. This basis vector may not have unit length, but we're going to do the dot product. We're projecting A down onto the direction of the vector. That's A cosine theta in length. But remember, when you make a dot product or an inner product like this, you not only get the projection of one vector onto the direction of the other, you multiply it by, in this case, the length of epsilon sub 1. So one of those epsilon sub 1 magnitudes in the denominator is going to cancel this one in order to return us to the projection A cosine theta. Those two things have canceled. But we said you have to divide by the square of epsilon sub 1's length. And why is that? Well, remember what a vector component is. It tells you how many times the basis vector fits into that particular direction of that vector. Again, I'll clean this up a little bit. So what we're asking is, in this length A cosine theta, how many times does this basis vector fit in there? Because that's what A sub x tells us. So in order to know that, we have to divide by the length of that basis vector. So one division takes care of the basis vector's length that appears in the dot product, and the other one gives us the vector component in terms of number of basis vectors that fit into the projection A cosine theta. That might be a little more clear if you look at this example in which I said, okay, so let's say A is a vector with length 10 kilometers. It's a real spatial vector in this case, and it has an angle of 35 degrees to the x-axis. When you project A down onto the x-axis, A cosine theta, you get about 8.2 kilometers. But let's say that our basis vector, epsilon sub 1, has a length of 2 kilometers. It's not a unit vector. The component A sub x is how many times this 2 kilometer basis vector fits into our 8.2 kilometer projection. When you divide 8.2 by 2, you get 4.1 steps, each of 2 kilometer length. So the x component, A sub x, is 4.1. Remember, it's not 4.1 kilometers because we divided the projection 8.2 kilometers by the 2 kilometer length of the basis vector. So the component is just 4.1. If you will, it's in units of basis vectors. Had that basis vector had a length of 1 kilometer, 1 unit in this case, then A sub x would have been 8.2 divided by 1. It would just be 8.2. So that's why you have to divide by the square of the norm of the basis vector if you have non-unit basis vectors. All right, if you do have orthonormal basis vectors, that is, they're orthogonal or perpendicular, and they're normalized, and this process is called normalization when you divide by the square of the magnitude, then you can write a nice simple relation between the basis vectors that looks like this. If they're orthonormal, then dotting any basis vector into any other, that is, taking the inner product between them, will give you this delta function. This is the Kronecker delta, which always has a value of 1 if the two indices are the same, and 0 if the two indices are different. So epsilon 1 dotted into epsilon 2 gives 0. Same thing with epsilon 1 dotted into epsilon 3, 4, or 5. But any orthonormal basis vector dotted into itself gives a value of 1. Most important for quantum mechanics, it works for functions. So here's a function psi. We're representing it as a vector, that is, as a ket psi, and we're saying it's made up of some amount of these different basis functions. The basis functions are psi 1, psi 2, all the way up to psi sub n. Each of those is written as a ket, and the amounts are given by these coefficients c1, c2, all the way up to cn. Here it is, using the summation symbol. So each of the c1s, 2s, and 3s tells you the amount of that basis function in function psi. And we can use the exact same approach we just did for vectors to find out what those amounts are. If you're given a function psi and you know your basis functions, psi 1, psi 2, etc., you can use this inner product. There's the inner product of psi being projected onto the first basis vector. Remember to take the complex conjugate of the first member of the inner product. And then you have to divide, because these guys may or may not be normalized, you have to divide by the square magnitude of that basis vector, just like we did for epsilon 1 up above. If you want to know the amount of the second basis function, project psi onto the second basis function, divide by the square magnitude of that second basis function, and so on, all the way up, however many different basis functions you have. This approach to finding the components of the function using sinusoidal basis function was pioneered by Fourier. This is the very essence of Fourier analysis. In quantum mechanics, we call that spectral decomposition. And that range of coefficients c sub n are called the spectrum of the function. Then there's an example where you can see this working. I've picked basis function psi 1, which is just a sine, psi 2, which is a cosine, psi 3, which is sine 2x, over some interval, which I made minus pi to pi. Then I wrote a function psi of x, which is 5 of the first basis function, and 10 of the second, and 4 of the third. Now you can just read the amounts right off here, 5 minus 10 and 4. But if you want to see how the math works, here's the approach. First we project psi onto psi 1. Here's psi with its 5 sine minus 10 cosine and 4 sine 2x. Here's the first basis function, sine x. We make that integral over the range we're talking about, which is minus pi to pi. And don't forget to divide by the square magnitude of that first basis function, which is sine x. There's that division. Same thing for c2 and c3. And in order to do those integrals, here's some helpful formulas. Notice that over this interval of minus pi to pi, sine squared and cosine squared both give pi, whereas sine cosine or sine mx, sine nx, where m and n are integers, give 0. With those in mind, you can plug in to the C1, C2, and C3 formulas shown on the previous page. This one was the one that brought up the pi. These brought up 0, and you're left with 5. Same thing with C2, you get minus 10, and C3, you get 4. Exactly what we would expect. Remember, just because you have sines and cosines does not mean they're normalized. A lot of students are somewhat surprised by this, thinking, well, sines and cosines go from minus 1 to plus 1. That's true, but the condition for normalization has not to do with the peak values, but the integral of the square of the function. And over this range, that did not turn out to be 1. It turned out to be pi. Okay. In this chapter, we started out talking about vector spaces and abstract vector spaces, how to expand vectors and functions using components in a specified basis. We talked about Dirac notation and a lot about the inner product in determining the components of vectors and functions. With all that, you're ready to look at operators and eigenfunctions. Those are the subjects of the next chapter. But I strongly recommend, before that, work through these problems. These little gear symbols down here mean the solutions are fully available, either in the app or on the book's website. There's also some conceptual quiz questions to just make sure you're getting the major concepts of this chapter. All right, as I said, I strongly recommend working through all these problems. When you've done that, you should be ready for Chapter 2. Good luck.